So, this is problem number 2 off of our chapter 6 homework. The premise of the problem is we've got a stoplight that's hung from two equally angled tensions at 37 degrees. So yeah, let's get right into it. The first part is it asks for a free body diagram. So here's roughly our situational diagram. Doesn't need to be, doesn't need to have a lot going on. For our free body diagram, we're going to call this our x direction and then our y direction. For this, always and forever, we're going to have our force of gravity right here, our Fg. And that's going to be our mass times, our G value, 9.8. Then we're going to have two equal angular tensions right here, each at 37 degrees. So let's get those guys in there. Make that guy a little bit longer. Cool. Call that theta for now. Theta equals 37 degrees. Sweet. That's the first part knocked out. There's our free body diagram. Now, for the second part, it wants to know the tension in each one of these cables. Essentially, if we call this guy T1, we know they're equal because their angle T1, T2, it's synonymous. So now you need to just find the force in each one of those. Now the thing here is our fundamental equation is going to be the sum of forces in the y direction is going to be equal to the mass times our acceleration in the y direction. We don't have anything going on in the x direction here. Yes, it does have x components in the tensions, but we don't need to worry about that because we're in equilibrium. It wants to know, sort of what's going on in the y direction, or up and down. Really, only because our opposing force with the, weight of our stoplight is acting downwards, not side to side. First thing it's going to be very important to solve for, I'm going to relocate this guy. We got to solve for that weight of our stoplight. And that, like we said, is going to be mg. So the mass, 20 kilograms, is given to us in the problem. 20 kilograms times 9.8 equals, should get 196 newtons. That's our weight of that guy. So we're going to replace this right here. We'll call it 196 newtons downwards. For now, we're going to call this guy negative 196. Sign is very important here because we're talking about equilibrium. So yeah, now we need to find how much essentially the y component is of the tensions. Now the thing here is, since we're in equilibrium, our sum of forces in the y direction needs to be equal to 0, which means our acceleration needs to be equal to 0. For this condition to hold up, we need to make sure, well, we've got two forces acting in the y direction here, in the positive y direction. So that means 2 times whatever that is, that upwards y component of the tension, needs to be equal to the opposite, or just 196 newtons. That being said, 196 newtons is equal to 2 times the tension in 1 sub y, called the y component. Now to solve this guy, we're just going to divide by 2. And for that, we're going to get 98 newtons is equal to the tension in the y direction. This gives us the actual magnitude of that force. Now we just want to know, okay, that gives us the y direction component. So now we want to, use our angle, our theta, to our advantage and find the actual magnitude of that force. For that to hold up, we're going to say, okay, our sine of our theta, 37 degrees, is equal to, call it our opposite right here. That's going to be what we solve for, that 98 newtons, divided by our hypotenuse, that being the magnitude of our tension. So now we can move this around. This implies that our tension is equal to 98 newtons divided by the sine of 37. for that, we get our tension, call these guys, you know, T1, T2, they're the same thing, equal to 162.84 newtons. That is it for this guy. Let's box our answer, call that guy good, and that's it. There's the tension.